I'm really happy to be here, and I know that I'm the last talk between the evening event, so I hope you're welcome to stay. This was an introductory investigation into using deep learning for space image enhancement. There's not a lot of work that's actually been done on this, so instead of our amazing talks this afternoon, this is a very practical approach to a relevant problem. Oops. Okay, so at present, there are 5,500 satellites in active orbit right now. And the thing is, they're not going to always remain active. They're going to go inactive. And what happens when that happens? We create junk. A lot of it. Right now, there's only a fraction of the satellites in space, but before too long, with the introduction of these new constellations, we're expecting that there could be even more than 5,800 satellites in orbit by year 2030, and that's significant. In particular, Kessler has estimated that beyond a certain level of critical mass of space debris, you only create more and more space debris through very consequential catastrophic collisions. So we need to address this because it matters to our day-to-day lives. In particular, I mean, everybody uses your phones all the time with satellite technology, especially if you're traveling by boat. Does anybody use a map anymore? Or is everything GPS? Imagine if the satellites go down in that context. Early warning systems for severe weather, tsunamis, all that kind of stuff also come from satellite information, our defense, our national security, and of course, our Netflix and entertainment. So it's a really big deal if our satellite systems are compromised due to space debris or whatever reason. The other reason, especially, and this is concerning to Luxembourg, is that whenever you register a satellite, the entity that registers it is responsible for the damage caused through collision. In Luxembourg, we're a small country that could virtually bankrupt us. Okay, the sad thing, I don't mean to be a doomsdayer, but collisions in space, especially with debris, are virtually inevitable. There have been occasions where the ISS was nearly struck. ESA had some satellites with near misses. It's just, we have to do something. So what can we do to mitigate the risks that we're facing? Well, one thing we can track in space, we can service and manage in situ. So we have satellites that don't run out of fuel, or can be, we can service them in space so we can prolong their lifespan, and we can remove the space debris. But in order to do that, we need to be able to actually make estimations on the actual pose of a spacecraft or the debris. We need to get more information about that. And we're going to do that using optical imagery. And the idea behind using optical imagery is, like, we're setting up a space lab in the groups. And this is really a cost-effective, simple solution. So it's really just, can we do this to begin with? So these satellites this is a synthetic generation of satellites. It's a data set that's been created in our group, and for the specific purpose of pose estimation. When you talk about capturing images in space, you have to think about the situation that's occurring while in space. We have the sun, which creates a very bright light and causes a lot of overexposure for images. But then on the opposite side, if you're not facing the sun, you have near pure darkness. We're also moving, the spacecraft are orbiting, and so are the planets. So there's a relative motion between the two. So that creates a couple of situations. First of all, you're going to have extreme lighting conditions. And that means if you're taking optical images, you're typically going to have overexposure, underexposure in a lot of cases, and not necessarily be able to see the features that we need to directly extract the pose of our space objects. Also, we've got harsh temperatures, extreme temperatures, and radiation. We can generate thermal noise, sensor noise. And finally, as I said, we have very fast moving objects. We have not only motion blur, which is pretty much inevitable, we have optical blur due to the poor focusing capability of our camera. Oops. I don't mean to have that extra thing on there, but. Oops. Okay. So here, these are just grabs, screenshot grabs of ISS images. So you can see that we have exposure issues, we have blurring issues, we have some noise. And so these are the conditions for which we want to correct. And the question was, yes, we applied classical image processing techniques to improve images, but like in the talk yesterday, sometimes it's not very efficient and it's not fast. So we want to look to other ways where we can actually enhance the images without specifically modeling the system, because it is fairly complicated. So can we use neural networks? Of course we can. We just need to find the weights, and that's the problem. So a major issue is that we don't have enough data. First of all, we're dealing with synthetic data, but also we don't have enough real data at all. And we also want to make sure that in our training set, we include the degradations relevant to what we're going to be experiencing in the actual space environment. So we augment the data set with what we think could be reasonable image degradations, including blur, adding noise, both optical and gain blur, that kind of sensitivity noise and that type of thing. So here's an example of some of the images in our augmented data set. We don't have a lot of colors, and yeah, it's pretty, it doesn't consider every single case of what you would typically find in space, but it is very normal that there's very bright places, very dark places, high contrast and noise. So the architecture that I used in this case was a UNet architecture. Instead of the original that was used for biomedical imaging, I have 3 channels instead of just 1. I've changed the image sizes and a little bit to terms. Instead, I do bilinear upsampling, and I investigate a couple different types of losses, both mean squared error loss and perceptual loss. The reason why I wanted to go beyond mean squared error loss. Okay. Okay, thanks. Is because I didn't want a pixel to pixel comparison. I wanted a feature comparison, because the structure is what I'm most interested in. So then in the interest of time and reducing training load, I took the encoder part of the UNet and replaced it with ResNet. I investigated both 18 and 34 level layers, and that's where we went. I used transfer learning because we trained the ResNet's pre-trained on the ImageNet database, and I wanted to see, okay, let's do a sanity check. Does it make sense to apply transfer learning to this particular problem, because we don't have that much satellite data in the data set? So on the right-hand side, if I was just going to use the base UNet layer, those are the features that I get. And on the right-hand side, these are the features directly out of the pre-trained ResNet model with 34 layers. As I said, I looked at a bunch of several different evaluation metrics. This is the procedure that I applied to generate these models. One, I used transfer learning, just like I said. I also investigated progressive resizing, so you could learn the lower level features first and then gradually increase the size of the image. But I must say that one didn't work out as well as I would have liked. And I think that might be simply because my images were too big and I couldn't include as many in the batch size thereafter. I alternated the learning rate throughout an epoch. And of course, if the learning rate wasn't changing, then I stopped after I lowered it so we could get out of any regional minima. And then because my data sets are so small, overfitting is a real possibility. And if the learning rate wasn't improving after a time, then I go ahead and stop the training process. Or I save the best model because it can, the loss can increase as you go on. And then finally, after a certain number of iterations, if it didn't improve, then I stopped the training altogether. Here you can see some of the indicators for the loss functions, or the evaluation metrics. The model that I chose to go along with in this case is the UNet-ResNet34 that's with perceptual loss. It's a feature-based loss, and the 34 layer. And you can, even though, and I'll show you, this slide kind of tells why. Here are the top two are basically, the first image has a little bit of color. The second one is purely grayscale. The model was trained for RGB images, so I don't expect perfect performance on the top two. And here, this is just blind inference on a minimal training of images of the ISS. And I found that the edges were better and with the perceptual loss. So that's what I took. I saw less artifacts in that case. And then here are just some image examples about what came out of the model. Look, so on the right-hand side, that was the input. I had a target, supervised learning, and on the left-hand side, that's what came out of the model. So it's pretty evident that the noise can be removed. And I guess I need to go back and implement new models that I heard about today. And so we were able to sharpen the edges a bit. That work needs to be done a little bit more, train longer, and separating content, changing contrast, so you could more easily identify some of the edges. But you see, in the noise is really the best that we've dealt with. And the big thing to remember, garbage in is garbage out. If you have in your target images that are not what you want to get out, or are not large enough to represent the features that you need to recognize, then it's not going to promote a very good result in the end. So here, this is blind inference compared against other deep learning models. Most of because there's not much going on for the space yet, these are mostly models that are attempting to correct dark image, lighten them, some to lighten images, some to darken images, some to enhance contrast, remove haze. These are the types of algorithms that I explored. I also looked into underwater methods as well, because they seem to care, they have some of the blur, some of the haze, some of the characteristics of images captured in space. And our method is the one on the bottom, the left hand, as compared to the other existing methods. And so I just went ahead and ran this on a few of these images to see what would happen. And yeah, luckily we don't have the blocking artifacts, and that's just, I think that's largely because we changed the outsampling scheme and shuffled the pixels around. And this model is not going to be deployable on a CubeSat at this moment. There's too many parameters, even though it's lighter than some. So we have to rethink where we're going to go from here, what the next steps are. But at least it was a first step to see what might be done, how might we do it, and where to go from here. We have to determine. I believe that deep learning can do a lot of things, but I also am a firm believer in traditional signal processing. And I think that combining both methods when you can really makes the most sense. If you, like yesterday it was discussed, if you have a physical model that is really representative, at least a part of what you want to model, go ahead and use that. It makes sense. And try to optimize your algorithms to attack those issues. The UNet, that's a good choice for image enhancement. It's an image to image, makes sense, but it is memory heavy, which will not be deployable for space. Multi-stage, to me, that's all. I worked a lot in compression and in doing a multi-resolution type of work, and I think that there's definitely applicability to that here. I think that loss metrics might need to be revisited, although, you know, we saw the great results just from the mean squared error today. So we have to think about it. It also depends on how long you train and how big your data set is and all that. Reduce for space in particular, we could crop the images. If we can do a quick identifier to the region of interest, put a bounding box around there, that will reduce the computational load. We don't have enough data, especially data that's really representative of what we want to model. So that has to be addressed somehow. And then the next steps, we need to develop better, lighter models for deployment in any kind of spacecraft. And finally, we don't want to create more space debris with our CubeSat that goes up in the planet here. So thanks so much for your attention.
Thank you very much. So we have time for questions. Yes, Anatole first.
Thank you for your presentation. As the low quantity of training data seems to be a problem, and that you tested your implementation with underwater images, I was wondering if maybe in terms of data augmentation, underwater images could be used to increase the quantity of training data.
Actually, I didn't test with underwater images. I looked at models that were being used to address the degradations found in underwater images. So I didn't actually train on any kind of underwater data.
Okay, thanks.
Otherwise, yes, I would have augmented with more of that type of data.
Thanks for the nice presentation. I had a question about the last point, one of the last points you made about the fact that model has like 46 million parameters and the fact that you cannot easily deploy it on a satellite. Have you been thinking about how to bridge that gap? I would be very interesting about, you know, how are you thinking about the question of making deep learning models deployable or more compact to be deployable?
Well, my colleague Carl in the audience is working on NAS. I mean, pruning models. We need to go further. I don't think the UNet is going to be the solution altogether, but we need to figure out ways to make more compact models. How can mobile net be expanded to function on image enhancement, that kind of stuff? I mean, is it even feasible? We have to rethink a little bit, but we definitely have to trim to make it even a possibility.
Other questions? Yes.
Thank you for your nice talk. I wanted to ask, so as far as I understood, this is supposed to be used on an onboard satellite mission. And have you thought about any methods for protecting against radiation-induced bit flips, or would that even matter in this case?
Most likely, this would be on a CubeSat, and even Raspberry Pis have gone into space and they've lasted it. I think realistically, for the investigatory studies, we wouldn't be putting it on anything really much larger than a couple U CubeSat. And with that in mind, we wouldn't have the space, the weight, we would have the weight limitations, and we don't have the propellant. And unfortunately, the reality about so many of these academic missions or investigatory missions is that they're not meant to last 25 years. They're meant to last like 1 or 2 years, which completely, you know, spits in the face of the problem that we're trying to address. You know, and the lack of radiation hardening is a big reason why satellites become unfunctional in space. So those are the most amount of radiation hardening goes towards the larger satellites, at least the smaller.
And so my question was also directed towards the kind of predictions you make, because radiation-induced bit flips may influence your predictions, so they might become unreliable.
Yeah.
Have you thought of kind of algorithmic considerations for protecting against that?
Well, it would be just the fault algorithms that are built in to the system.
Thank you.
Yeah, and ideally there would at least be some redundancy.
Another question? Thank you very much for the nice talk. I have a question, possibly not related to your deep learning, but as far as I know, the challenge, the most important challenge is just the small parts under 10 centimeter debris. So this is under the resolution of most of the optical telescope, whatever. Do you by any chance know what we can do with these very small objects, which are billions of them are just at the moment in a space?
Yeah, there are some net proposals and things like that to like scoop it in. There are a lot of different approaches. This is a multi-tiered solution. It's not one size fits all. But yeah, you have to think outside of the box because yes, you're correct. I mean, how are we even going to grab onto one of these particles? So instead, I think some of the net approaches might be more sensible in that case. But you've also got to make sure that you're not scooping up things that are supposed to remain in the air. And you need to accurately identify what needs to stay, what needs to go, figure out all the orbital parameters that when can you do whatever it needs to be done.